Okay, good morning. How are you? You sound very tired. Okay, so you may already see your homework grade. If you have any question, please reach out to TA first. And then like if you still have question or contact me. But I told TA if some of you just copy the answer from my previous version, just give you 0. Okay, it's because it's easy to know if you just copy the answer. I changed the problem, but you didn't change the code. Okay, so even though the answer is exactly the same, but like if you didn't change the problem setting, which means you never understand what you are doing. Okay, so but I'll change all the problems next time. I won't let you try to find the answer directly on website or some other stuff. I'll try to do that. Okay. All right, so let's go back to what we tried to start this week. And so actually I'm trying to assign some homework, but I just felt we can finish some parts. So maybe I'll assign the homework next week. And then that will be the part, like I guess just the last assignment before the midterm. But still maybe we'll have some other new concepts or new questions in the midterm exam. Okay. So even though I haven't decided the date, but I will still I hope I can stick to the October 12th as the date for the exam. Okay, so we will try to do that. All right, so this part we will learn the pseudo random number generator. How can we try to generate that? So here is just give you some ideas. Okay, so and also one important thing is not say you know how to generate that, you know how to to check if this is a good or bad pseudo random generator. That's more important than say let's you try to do it. But of course we'll learn some other ways to try to generate some random variable follow different distribution. That's the important case. Okay, you need to know how to do that, no matter it's the theoretical way or you try to generate that or you know, of course you need to understand the theoretical way and then you know how to generate in MATLAB or in Python. You can try to find a way to generate this. Okay, so one easy idea to generate the pseudo random number is called this linear congruential generator. So the idea actually is you choose a very large or huge integer. Okay, this one can be pretty large because if it's small, then you can only generate some simple random numbers. So, and then you will choose 1a to be a large primitive root of this m. So what does that mean is you do the modulo of this, all the powers, okay, modulo this, and you will never get 0, okay? So for that case, most time you can choose this big M as a prime number and choose a big, large prime number, so it will be 0, okay? And then this M naught is your integer seed. So we will try to have our pseudo random sequence. So you know if you have this M, right? Because we consider how we try to generate this random number, it's always uniform on the interval 0, 1. So which means you can generate is 1 over m, 2 over m, until m over m minus 1. But it's not just follow the order I just mentioned. So 1 over m, 2 over m, and then to get m minus 1 over m. No, but you will find a way to get that. Okay, so that's the way we try to do this, is use this m naught as the integer seed, and then you're trying to times a with that. And after this, you do the model and do the modulo, and then use this part to over this. This will be your mi, new mi, and then use this mi to over the capital M. Then you can get this. So we see this case. So last time we already introduced this one, right? Because we choose m naught as 3. So we try to get m1. So how can we get this? Because 8 times m naught is 21, modulo 11 is 10. So we get this one. And then how do we get xi? It's 10 over 11. That's the case. And then we can keep doing this. And you know this will be a cycle. At some points, it will finally come back. But of course, this one is good because it can reach all the numbers. So why we want to have the primitive integer? Because we want to avoid at some cases, maybe at 4, then you already come back to the original number. Then that's not a good one. So here, if we choose m is 11, we can choose a is 7. That's the primitive root. But of course, you can also choose a is 6. Like try to see what you can get, and we will see that. So there will be some other values. You can try to figure out a way to do this. Okay, then what is the idea of pseudo-random number? If we just consider on the interval, of course, we want to have the kind of like evenly distributed, but it will be a little bit better trying to show, like, for example, like in the square term, or like in the space, the hypercube, to show if you order that, it can have a good random numbers, can fill the whole square. So we will discuss 2 tests, okay? So this m can have many primitive roots, but not all of them can have a good pseudo-random number. So for the square term, it's easy for us to visualize that. And then you can also consider for high-dimensional case, you still try to generate this, or like all the sequence of the random numbers, just follow the way we introduced, but you can consider to truncate it at like the dimension. So for example, first 2, next 2, and then keep going, like this is for the square. Or like for dimension D, you just cut it into several pieces and then try to generate in the space and to see how does it work. So for this one, so if you check this 2, which one is better? Okay, second one is better. Why? So yeah, it looks like, so of course both these 2 have some like patterns there, and then this one looks better because it can spread out a little bit compared to this case. Okay, so we will try to define one way to kind of to do the test. So we know the second one looks better because it can be more evenly distributed, or like it can spread out on the whole screen. Okay, all right. Oh, sorry, I don't know what happened. Okay, so one is called spectral test. This one is trying to show where all the points you have to fill on this whole space. Okay, so this will be considered as the largest possible distance between planes covering the points. So for example, you will consider, say, let's try to, of course, this is the largest possible distance. You won't consider, say, let's connect the 2 points like kind of like vertically to see the distance. No, but here 2 parallel plane, then of course we can cover this, or 2 parallel lines, we can cover this or all these points here. Then the largest distance will be this red line. Okay, and then for the second graph, if we try to use 3 lines, parallel lines to cover all the points, and we know the distance will be this red line, and of course this one is shorter than that. So if possible, we hope this distance as small as possible, right? And then of course, right now we don't have a lot of points, it's just 11 points. So that's 10 points we have here. So that's what we get. But if we can have more, then that will be, the distance will become smaller and smaller. Yes. Or this is just give you the idea. You won't be asked saying which one is better, and then you try to draw lines and then do the distance. No. So here is trying to give you some ideas, like even though you don't like, here is just trying to show the parallel planes and also the distance. Even without that, it's still easy for you to know this one should have smaller distance compared to that if we choose the largest distance there. Okay, but that's actually give us the idea is you hope the points can spread out on the whole space or on the square. That's it. So we can try to check it. Okay, here we have some bad random number generator in MATLAB. There is a fun function. It's called randu. This one can generate different numbers, but we won't use that. Okay, so most case are because it's not always to be really random. So let's consider what we try to do here. So why that is not so good? Because this will give you this random numbers. So if you just do 1D case, everything looks good because you cannot see a lot of patterns there. But if you try to convert it, like do this as the similar way, order them in pairs, and then plot these points, then you can see here, they actually concentrated to some area. These are not really spread out on the squared parts. So this is not so good. Because if you generate this, which means you can only catch the information at this point. So, and there are a lot of blank space here. That's not random. Random at least should have some points here and then there, right? Not like just, it's very like similar and then also parallel to each other. So this is some bad example. So now if you try to do some like, I know Python and a lot of some other like programming language will have their own like random number generator. So you can use similar way, like trying to like generate this and plot it, try to check if it's good or bad. So you have some sense of that, then it's okay, right? Okay, and another one, this one is a little bit complicated. So even though we hope this can are of course spread out on the whole space, and we don't want each of them will be too close, just like what we have here. So this two is a little bit too close. We hope it can have like not too close to each other. So you will consider if we generate some random variable here, and this will have the cumulative distribution function f. So we have this one, and this actually is also important when we to learn the inverse transformation there. So this one, the cumulative function, if we assign for each yi, we get its cumulative distribution like property of that, probability of that. This will be an xi, and this xi should be a uniform, standard uniform random numbers. Does that make sense? Because you choose different yi, so you calculate the CDF of that, you will get some value between 0 and 1. So because your yi generates randomly, so then your xi corresponding to that should also be like random. So that's why it will be uniform on 0, 1. So this is your xi. And then you try to define your zi just in the pairs, just as what we did before. So consider d dimension. And then you will still have the z will have like d elements inside, and then how many zi you can have is from 1 to k. Depends how many sample points you can generate and divide by d. Of course, you just make sure this will be an integer. Okay, and then what is your zi? Because this xi is kind of like the random number you generated, and then you try to generate zi, then zi should be id on the hypercube there, so you will have that. So you are trying to break this hypercube into L, so non-overlapping bins with volume L minus 1H. So it's kind of, you try to cut let's just consider a cube, okay? You try to cut this cube in several pieces. And of course, these pieces will be L pieces, and each pieces will with the volume is 1 over L. So which means with the same like volume inside, and then you try to see how many zi inside this bin. Try to check, because you don't want to have a lot of like zi on the same like bins. So here you will assign another value is called w. This is number of bins containing more than 1 zi. So the best case is, or if you try to have this bins, so each bin just contain 1, that's ideal case. And you can cut, and you can cut as many as, of course, it depends on how many points you have, right? Depends on this case. So of course, it depends on this one. So depends on k and l. So that's why we try to do is k squared over l is equal to lambda. Then this w should follow the Poisson distribution. And when k goes to infinity, when k becomes larger and larger, so that will follow this Poisson distribution, which means the number of bins actually should contain the number of zi should equal to this lambda we have here. That comes from what we have. So what we try to do is to check this. We don't want a lot of, for example, we don't want to a lot of, for example, the expected value is lambda. We don't want like in one bins, it can contain like maybe 10 times lambda CI inside. Or like in some bins, like we only have 1 point inside that bins, but that's not the case. So it will depends on this value lambda. Of course, it will depends on the K. So you're just trying to observe this W. If it's like a bins contains more than 1 CI, so this value, it depends, okay? So it will depends on your lambda here. So if this x1 to xn is much larger or like or smaller, so when you have then this mean value, this W is too larger than this lambda here, then we will have some issue for that case. So this is the idea like we have. So for actually the idea is the same thing. So you can consider it can be more evenly distributed. So at each pieces, it should have one. But if some bins have more than one, then which means in that part, there are several or ZI, they are very close to each other. You didn't really, this is not really the random like numbers generator. So that's why it will have some issue. So this is the collision test. Okay, so just give you the idea, but actually when we move to the solvable points, if we just consider 2D case, the one nice property is, so suppose we have 64 points, then you try to cut this square into 64 pieces, horizontal or vertical, or you try to do some combination, say like 8 by 8 or 16 by 4 or 4 by 16 or anything, you try to do this combination. Each bin, or not bin, yeah, it still can be a bin. So each bin can contain 1 point, always like that. That's the good property of solvable points. So that's why we want to have this kind of like nice property of these points. But of course, solvable points is not like the IID case. They're pseudo Monte Carlo, like the quasi Monte Carlo, not pseudo, quasi Monte Carlo points, not the Monte Carlo one. Okay, so just have some ideas which one is a good case, so which one is a bad case, then it is okay. We won't do some questions really related with the collision test or this spectral test, but you understand the idea of that. Okay, then we move to some important part is to generate this non-uniform random numbers. Because we play a lot is under uniform or like 0, 1, of course, we know how to generate that. So that's the basic case. And if we can choose a big or large M, then we can always try to generate the standard uniform. And then based on that, we can try to generate some other random numbers. So that's the case we want to do. So the simple one is the multivariate uniform random variables. So for high dimensional case, what we can do, of course, you just trying to change the dimension. D is the dimension, N is the number of vectors you want to generate. If we want to do like if it's follow the uniform distribution with vector A and B, then of course it's not so hard to generate that. So this is the idea. Then how can we try to implement in MATLAB? So let's see this one. It's not so complicated. So this is the case. So actually here, you try to initialize this scale, and then this is use the BSX function. Actually, to be honest, I don't quite like this function. So you're just trying to consider, okay, how can we use this function? So you can use this function directly if you are asked in your homework. So, but also you can try to do it by yourself. It's not so complicated. So this N means the number of vectors you want to generate. And AB, so this means is a box you try to have. So you will define this as this one. So of course, this is just 2D, right? So, but it doesn't mean like you always have that 2D case, okay? So here, you can see like this is to plus the first row. So which means this will be your A. So this is A1, A2. This is your B1, B2. Okay, so you plus the first row to that. That's how we try to do it here. And then you will do a times. Times is the difference. So you're trying to have the difference of this part. So that's this at times the difference. And then the random is what we have here. This is our Z. So this Z actually follows the standard uniform. And then this N is the number of vectors you try to generate. Then what is this D? This depends on the size of your box. So it's 2 by 2, then you know, okay, I just need to 2 dimension. That's it. If you have a box, it's not 2 by 2. So of course it depends on like you when you put this box, you will always have A, B, like so it depends on your size here, like how many dimension you will have, and then it will get you this number of like columns to have that. So that's the size. So you will get this is 2 by 2. Okay. So here it trying to generate is 300 like random numbers. And then where's the plot? Why I didn't have that plot? That's weird. So this is some vectors you try to input. So you will have all this. We try to put these points, the first column, our second column, and then to put these random vectors and axis. Here I only have this normal. That's really weird case. Okay, but you know you can use this function. Let me see if I can run this one. So most case, this is generated by the HTML. Okay, I'll try to figure out that. I don't know why this one we don't have the plot. So this is trying to show the plots of the random numbers. So which means when you generate this, of course, you try to plot it and to see if it works, trying to see if it's really satisfied. But also you can try to check the average, like the mean and the standard deviation to see if it's the right thing. Okay, this is for the multivariate uniform. It's not too complicated. Even though by yourself, I think you don't try to generate that's the general function. Based on different cases, it's easy for you to construct that, right? It's not so hard. But this one will be a little bit complicated. It's for the multivariate Gaussian random vector. So standard uniform, standard Gaussian, you have that. So, but if you have some X, so here X follows the normal distribution with mean is the vector M. And then a covariance matrix is sigma. So the first step is you trying to do a Cholesky decomposition of this covariance matrix because it's positive definite, so you will get this A. So we can do that, or we can also trying to do something like this. You will have this unitary matrix, and this unitary matrix has a lot of good property, but it's easy way do Cholesky decomposition. Okay. So I may give you some question. Okay, ask you to do it by hand, but say give you a covariance matrix. Of course, I won't ask you to do it by hand to do the Cholesky decomposition. Use MATLAB or use any other programming language to find the matrix A, and then you know how to do it in the following steps. Okay, so after we have this, then you will have this X well generated from this M vector and plus A times Z. So it's similar idea actually as this case, right? But the difference is this is a scalar. So you try to do that is kind of you have a different scalar to time to different dimension. But this one is a matrix. You times to the Z. Z is a vector here. So you can consider this X will be a linear transformation of that. And X, of course, is also a Gaussian random vector. And we're trying to verify, okay, this is true. So we do this expectation of X. This is easy. M is a constant, take it out. So A times expectation of Z, that's the matrix. So Z has what is the mean? It's 1, right? So oh, it's 0, right? Sorry. So this is the standard or normal. So mean is 0 vector. So this part gone. And then for the covariance here, so X minus M, this is your mean. So times the X minus M transpose. This is covariance, but actually this is a variance, right? So variance of x, so expectation is x minus m times x minus m to the transpose. And then what is x minus m? So you plug this a times z inside, and this is the transpose of that. So z transpose times a transpose, and z transpose times z transpose here. So you will consider, of course, a is a constant function, has nothing with your expectation. So you will just put this expectation inside here. Then what is z times z transpose? Because its mean is zero vector. So this one actually is exact the variance like definition of z. So it's also the covariance. So covariance of our z, like if for its 1D case, then it's variance. And if it's multi-dimension, it's covariance of that. So we know this z follow the normal, standard normal. So the covariance matrix is the identity one because only have the diagonal is 1. So we will have this is I, so it will be A times A transpose. It will come back to sigma. That's what you have. So here is just to show you how you get this case, okay? Then let's go to the example here. So I change a little bit. If you download the previous version, maybe you will see something a little different. Why I changed that? Because I want to make the notation consistent. The previous version here, this is z, this is x, so it looks a little bit weird. So I make this consistent with our slides, and also we always consider z is like standard normal. That's the case we always try to do, right? Like z value, z scores, or something like that. Okay. All right, so here is just trying to show you what happened here. So this to get a covariance matrix. And then, so here, let's consider one positive definite matrix, sigma. This is not too complicated, 2 by 2. Okay, but of course, Cholesky decomposition can do more than that. So this is gets the eigenvalue of that. So we output sigma gets the eigenvalue. So you can check. Why we want to check the eigenvalue? Because for the positive definite matrix, we know all the eigenvalues should be positive. If you see something negative, then something wrong. Okay, you cannot do that. And then here we just define this Gaussian. So this one is very simple. N is the sample size, so number of vectors you want to generate. And be careful here. We generate is n the one, it's the one row, it's a row vector. It's a little different from what we generate. The sign say the vector is a column vector because n is the sample size. So, and then this m is a vector. Okay, you want to shift. So it depends on this x follows the distribution, right? So this is the vector here. And then what is B? B is the matrix. So B is the matrix you try to generate from Cholesky decomposition based on your covariance matrix. Okay, so here is like plus, which means m plus this terms. And then this term is you use this n and m trying to generate the size, okay, and times b. So m give you like the dimension, how many vector, like what is the dimension of that? So you will get our number of columns. So you will get that. And then you times b. And be careful. Why here we use b? Because most case we use a times z. But right now z is transpose. So we should use z transpose times a transpose. So this is no longer the original a, okay? Because right now this is a row vector, so we should multiply from the right-hand side. Is that okay? All right, so I know it's a little complicated, but this is the way how MATLAB to generate that. So we generate like this case. And this is to get the Cholesky decomposition. And then we will use that multiply from the right-hand side. Be careful here. Okay, and then you can see here is B transpose times B. So here B is actually A transpose. Okay, and transpose you just use prime, then it's fine. So M we consider is a vector with minus 1 and 3. Right now we also use the row vector to make it consistent. So this is how many columns we have. So it will have, you can consider 1 row, 2 columns. So we have that. Okay, and then this is trying to generate what is the sample size? So 1000. And then we have M there, and this is B. That's the matrix we get from the Chelsea decomposition. And then we're trying to plot these points, okay? X is the first column, and then Y is the second column. So try to combine them together. And then to emphasize or to specify this X's here. Okay, so if we check here, so this one should follow the normal distribution with mean is -1 and 3. Try to see if it's centered at -1 and 3. Seems good. Okay. And then what about the covariance matrix? Then we need to check that. So we do this mean. Okay, of course this should close to M, but of course you cannot get exactly M. And then the covariance of that. And actually, if you rerun this file, you will get a different answer. Definitely, because you have this randomness inside. But even though it will be different, but this one should close to -1, this one should close to 3, and this is 2, 1, 1, 1. It's not exactly the same, but it should be similar to that. Okay, so sometimes if I ask you to generate some random variable, if it does not satisfy like the uniform or Gaussian, then you can use similar way trying to check if you have some information as its mean and its variance. So this is a good way for you to check if it really generates correct random variables like that. Okay. Of course, this cannot guarantee you always do it correctly, but if this does not satisfy, which means you got this totally wrong, right? So you need to go back to check your code. Okay. So here, I actually give you another one to generate that. So it's consider we use this unitary matrix. Okay, and the unitary matrix will satisfy transpose times itself is exactly the identity matrix. And then you try to write this sigma as C times C transpose. And then you will have C is equal to A times U transpose there. So another way to find it is you will try to consider your singular value decomposition. Does that sound familiar? Okay. So for this case, you will get singular value decomposition. So this one will be a diagonal matrix. And then you will have U and B, their unitary matrix. Okay. And this diagonal matrix, of course, will always are non-negative entries there. Because sigma is symmetric. So actually our singular value decomposition does not just work for this covariance matrix. You can always try to do that. But because this covariance matrix has some property, so that's why when you use singular value decomposition, you can also get some nice property of that. So this will tell us U actually is exactly equal to B because it's symmetric. So that's why you can consider you take the transpose, right? So transpose, then it will be B times our sigma times U. This is the diagonal U transpose. Then because this is the diagonal, it's transpose itself. And then this two should always be equal. So that's why U will equal to B. That's the case. So what you can try to do is when you do your singular value decomposition, your A actually is you take the square root of the diagonal matrix times U. This is unitary matrix. Then you get that. So this is a different way to do it instead of the decomposition. It may be a little bit complicated, but you can try to do that. Okay. So here we try to do a SED. So this is singular value decomposition. Try to get this U and gamma. Sorry, that's gamma is the diagonal matrix. U is what we have. And then we take the square root of the diagonal gamma. So you can see it as DIAG. What does that try to do? If you have a matrix and you do the DIAG addition to that, just extract the diagonal element, and then it will be a vector there. So you take square root of that, of course you want to do it, and then do the multiplication. And be careful here, it's just trying to multiply or this one to U transpose, which means we actually do is the same thing as we did before. This is B is actually a transpose. So that's why it's times U prime. Okay. And then we have this case. And we can so here what we try to do actually is get this B, a different B, and to see what happened for this one. So this time B is a little bit different. And then but we're trying to check if transpose times B is exactly the same as polarity matrix. Yes. And then we try to generate this point. So you can see this point actually will be a little different from what we have before. Right? But of course we know it should center to minus 1 and 3. So we check this mean and polarity here. So minus 1, 3, 2, 1, 1, 1. So it's supposed to be close. Okay. So for 2 by 2, we cannot see a lot of like advantage of this singular value decomposition. When we move to high dimension case, singular value decomposition will give you like put more important stuff at the first step, like diagonal. So try to order it. So you will get this one, and then you can kind of like get rid of some not important information. That case that will be a good one. Okay. So we'll see that later. Okay. So actually these two are like two random vectors we are familiar with. Either uniform or Gaussian, and we don't need a lot of like transformation. Just do the shifting, stretching, rotation, and then you will get that. Right? Why the Gaussian is patient? Think about 0, 1 is just centered there. You try to shift it and some rotation, so you will have this center at minus 1. That's the case. So that's what we try to do. Okay. Then we will move to something actually a little bit more complicated and something new. So it's not like something you maybe already learned, but still it will do something we learned before in the probability. So same idea, inverse distribution transformation. So how do I try to do that? Okay, X is some random variable, but this time we just need it can be right continuous. You will see that why. So this one should have a cumulative distribution function is F. And this doesn't mean this one needs to always be a continuous random variable. No. It can be discrete. So just need the cumulative distribution function is right continuous. Okay. So and it's non-decreasing, of course. So then we can try to do is if you have some Z, this Z follows the uniform distribution. And then you can plug this Z inside to the inverse function and can generate X. So that's the idea. So why is this F is so important to be right continuous? Because we hope we do the inverse can be left continuous. We can find the minimum value of this Z. So actually the minimum value, this one, minimum value of X. So we can satisfy this one. So this looks a little bit complicated, but actually you can consider it is like you have some X such that the smallest X can make this cumulative distribution function is greater than or equal to Z. We will see some example like both the discrete and continuous. Now you know how you can do that. Actually, continuous it will be a little bit easier because you do the integration and then try to find the distribution function, do the inverse. But if it's the discrete, then sometimes you need to figure out a way how to construct the mapping because it will be a little different. Okay, we'll see that. So that's why we hope this is right continuous. Otherwise, we cannot get the smallest value of this X. If it's supermode, then it's not good. We want is the continuous, so we have this is the minimum value. So this tells us we want to generate actually is X. But we will start from this or standard uniform random vectors, and because of this X, we know it follows some distribution function. We can find its cumulative distribution function and do the inverse. Then we can figure out this X how to generate that. But then this actually requires lot of things, right? We need to have the cumulative distribution function, and it's easier for you to do the inverse function. Sometimes maybe it's really hard for you to map it back. You can use some nonlinear solver to find it, but sometimes you cannot just construct the function like as the elementary function directly. So the disadvantage is sometimes it can be very slow to find the inverse. So this is the idea. Okay, then let's see. This is some justification, but we can consider why this works. So cumulative distribution function, this one can come from your random variables can come from like all the real lines, right? But you're mapping it to 0 to 1. This is okay, right? No matter any kinds of random variables, you should always have that because the probability is either from is always from 0 to 1. That's the case. So then you're trying to map it back. So this is the inverse function, and then you do 0 to 1. Maybe it's the open case here, and to this R, and this one is non-decreasing. So always, right? So you cannot say if 0.1 I get 2 and then 0.3 0.1 I get 2 and then 0.3 I get 1. That doesn't make sense. So you cannot do that, right? You cannot make it decrease. Then find the definition. Of course, this is the cumulative distribution functions definition we have, and similar here. So this properties tells us how can we try to do it. So if we have z is from 0 to 1 and x actually comes from all the real numbers, then z less than or equal to f of x. This is the definition we have here. Okay. This tells us, okay, x is greater than or equal to this f inverse of fx. So this is come from what we have here. And then here, because z is less than or equal to f of x, so we consider this inverse function is non-decreasing. Then we take inverse, this one should less than or equal to that. Okay, then we have everything there. And similarly here, so f inverse of z should less than or equal to x. That's what we have based on the first line. And then we try to do the cumulative distribution function. We know this is also our non-decreasing function. It's actually should increasing there. So z is exactly equal to less than or equal to take the cumulative distribution function of that. So this one should be less than or equal to f of f inverse of f of x, and then this is f of x. Okay. So that's what we have. All right. Then we can conclude is this actually less than or equal to this f of x here. Something not quite right here. It should have one more term because the input for f inverse we don't have x input. But you can consider this is f inverse of f of x. Okay, I'll fix that. Okay. And then d is less than or equal to f of x. And it's equivalent to the f inverse of d actually is less than or equal to x. So that's what we have. And then if we have any cumulative distribution function, so we just let x is exactly equal to the inverse of this z. And then we try to show the probability of this x less than this little x should exactly equal to the cumulative function of this x. So we have this x to satisfy that. Then we make sure this is okay. We can do this kind of transformation. So it sounds a little bit theoretical, but the most important thing is how we can try to use this method. So if you one idea is about this mayor election, this is the district one. So let's see how can we try to do it? Okay. So this one is a discrete one. So we consider we try to do some election in the Chicago mayor election, and of course we have a lot of candidates. So and assume no candidates can receive the majority votes in the first election. So we will have the top two candidates, okay? And then, of course, not all the voters will vote. So one may wonder if the two top preferred candidates will actually be chosen in the initial election. So we try to explore this. Of course, this one will have a lot of like assumption here. So we have two top candidates. So the top two will have exactly the same probability to be selected, and then the third one will be very close to it. It will be 0.125, and then decreasing and until 0.05. And of course, this is your probability massive function here. Okay, we are not done yet because all the summation should equal to 1. So that's why we do one more part. So we have some other candidates, or maybe some other candidates, someone left, and then we will share some probability like this. Okay, so this is a massive function. So we do some assumption here, and this is discrete, and then we try to see the result. So you can see our first three like close to 1 or 13%, and then it's decreasing, and at the end we may still have some other candidates. All of them will share this 2% probability together, and then we try to do some like to check if it's really 1, of course, and you can use sum. This is to get the cumulative distribution function of this random variable. So let's just consider this random variable will have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 candidates like have that's their numbers, and then we do the cumulative distribution function. So sum them up. Okay, and this is the end file. So we want to see if the top two can be elected for the first like initial round. So how can we try to do it? Okay, so here we suppose this votes is 5 times 10 to the 5. Okay, and then here is yes, 2 best win. So what is that? So if we have a function. So n trials, n votes, and the CDF, these 3 are the input. So n trials means here we do like 10 to the 4 times. This is the trials we have, and votes here, and then this is the CDF. So yes, is we trying to initialize this vector. This is the size of trials to see is true or false. So it's being selected for the 2 best. So this is where initial everything is 0, and then a candidate. So we will consider size will be the CDF or 2. This means CDF is what we have here, the cumulative distribution function. 2 is the number of columns. So we know that's 11. So we get how many candidates we have. Okay. And then votes actually will be the candidates for each of them. So everyone can only vote for one person, right? You cannot say let's do for like choose 2 of them. No. So that's why we will initialize this based on the size of the n candidates here. This is a vector. So initialize this votes. And then we try to do for each trials to see the votes. How does it work? So for each case. So here, this is the rand number and votes, okay? And we're trying to check if it's this one. So which means we generate a uniform random number to check if it's greater than the CDF. So CDF is the cumulative distribution function. So it's kind of like we compare if this uniform random variable is greater than that, we will consider it's voted for the student, not student, for the candidates. Okay, so you're trying to do that, and you get this sum. We generate this random variable and compare with CDF. But be careful, you try to sum them up, is you try to find the minimum value of x, right? So such that is greater than this case. So you're trying to check if this sum them up and then 2 plus 1. And here, and we have n candidates, and to check for different votes what is the sum of for different candidates? Votes is exactly equal to I. So yes, it's vote 1 is greater than all the others, and also vote 2 is greater than all the others. So we're trying to check if that's the true case. So you do this, and then you will have the n trials and votes, and this will return your binomial. Actually, it's the Bernoulli vector because you will have either 0, 1, 0, 1, so true or false. Then we will use this one. This is the binomial CI. Recall this one. This one is when we try to construct the confidence interval for a probability. If we convert the problem to be the Bernoulli, like from Bernoulli to binomial, and then we will check that. So we do n trials so for, which means 10 to the power 4 times, and to see how many yes we have. Okay? So to construct the confidence interval, the top 2 will win. And we can see the chance the top 2 win actually is 99% to 100%. And the elapsed time is about this. So which means the first 2 has a very large chance to win. And then this time we try to set this the same for the suburb here, but then the votes, like it will be a little bit smaller. So we will try to see what happened, and you can see for the suburb, if you have fewer votes here, then this will be affected. So which means when you can have more people to vote, so some people who have large probability to win, it will have more chances to win. So if you have very fewer people to win, then it's possible some other situation will occur. So it's hard for you to really have satisfied this CDF part. So this one will be much smaller. That's the case. But here it's just trying to show you one example, how to try to map it. Let's see some other example here. This is a computer example you can see, but we will also have some other example here. So this is trying to show you how we can really do the mapping. So for example, we have some cases. This x can take the value from 0 to 6, and it will have a jump at 1. So which means at 1, it will jump from 0.2 to 0.4. You can consider it will be continuous from 0 to 1. And when at 1 actually hold the probability is 0.2. So it jumped to 0.4 here. And then keep going. And then when it reached 3 to 4, so which means no values actually can occur from 3 to 4. But then it will still increasing. So it will be a piecewise function. It's still be okay because this one is right continuous because you can reach this value, but you cannot reach value here. Okay, then what is the inverse function of that? So you can consider the F inverse. So of course, if you give 1, you should map to 6. But if you're trying to consider some value here exactly equal to that, so be careful for this F inverse function. So what is your input? Actually, it's Z here. So your Y vertical, actually the Y-axis is your X right now. This X-axis is your output. So how to map it back, okay? But want to make it consistent so you can see that. So you will choose Z actually along this Y-axis. So if it's somewhere in between Z3 to 1, then you just map directly to that value. You can get it. But if you map this one to here, you cannot choose 4 because minimum value to get this probability is 3. So that's why this one will be left continuous. This one will have kind of a jump from here to here. So you will get 3 here to equal to that value. Is that okay? Does that make sense for this case? Because we find this x should be the smallest value to make that cumulative distribution function equal to z, not the largest one. So that's why it will jump. We know actually no other values can be taken from 3 to 4. So we get this case. And then keep going here, and you will see something a little bit interesting. Is if you generate any value from 0.2 to 0.4, you will get all the values. I say this is 1 because it looks like that. So it's a vertical line here. So no matter what value you generate from point 2 to point 4, you always get is 1. Because 1 can have this jump here. So that's why this is a vertical line. Okay. And then for other case, so for example, if C1 between here, then you just map it to here. So for this one, actually give us some like extreme case. Either you have a jump at some point, or you have some part you never take values at that point, and then you will see how you can map it back from this inverse function. Okay, but of course, we need to find this inverse function, even though it still can be piecewise, but you need to be able to write it as some like a function, then it's easy for you to know how to generate that. Okay, so this, hope this is clear why we need to write continuous for the cumulative distribution function, and for the F inverse, we need the left continuous. That's the case. Okay. Any questions regarding this one? No? Okay, before we move to that, we can try to see some example. Do we have time? Yes. So let's just consider some simple example, like say, let's to do it, where's my Jamboard? Okay, let's just consider, let me see if we have that here. Oh, yeah. Let's see this one. So I think this will be easier for you to understand for the discrete case. So for example, we have y can take 4 different values, 0, 1, 2, 3. And of course, this is a massive function. So the sum of them should be 1. So we have for 0, you can take it 0.2, and 1 is 0.4, and 2 is 0.3, and 3 is 0.1. Okay, and then the cumulative function will be 0.2, 0.6, 0.9, and 1. All right. So here, let's try to plot this F cumulative distribution function first. So when it's less than 0, we know it's always 0. When it's equal to 0, because it will have a jump, right? So it will goes to 0.2. So it's a step function. And then when it reaches 1, it will go to 0.6 because 1 has the probability 0.4. And then keep going. And then we reach here. So the blue line is the cumulative distribution function F. Okay, then the question is, so for example, if I say I choose a z follows the standard normal, right? If it's 0.5, can you tell me what is the value is x? So if z is 0.5, what is the value of x? I heard 1, right? So that's the correct thing because you see this red line is the inverse distribution function of that. So which means if you start from 1 to here, this actually is 0.9, I think. Yeah, 0.9. So if it's from 1 to 0.9, you will get the value is 3 because 3 is the smallest value, actually can reach that probability, 0.9 to 1. But when you move to 0.8, then you should choose is 2 because that's the one from this 0.6 to 0.9. So you will get that. Is that okay? All right. And then if you jump from like 0.2 to 0.6, then similar, you will get 1. And similar here, you're mapping it. So of course, you will trying to consider the smaller one here. So this one will be 0. So if it's from 0 to 0.2 and not exactly equal to 2, then you will get this is 0 here. So that's the case. So you can see if we generate the uniform random numbers, you know how to choose how to generate this random variable x or y here we have. Is that okay? So you just consider to map it to the smaller one. So for example, if I have 0.19. So what value I should have? 0. If it's 0.541, if it's 0.7, then that's 3. If it's 0.95, then you should generate is 3. Is that okay? Does that make sense? Okay, so that's the idea, okay, how to generate that. Okay, and you will see what happened for this case. So we try to generate some random numbers. So we have 0.5511, we know that's 1. 0.02, that's 0. And 0.08, this is less than 0.2, so 0. And this one is close to 0.6, but less than that, so 1. And then this is 0.2, greater than 0.2, still 1. This is 0.93, so it will be 3. And this is 5.9, so we get 1 and 0. So here, that's the y we can generate corresponding to x. Okay, so that's how we try to generate for the like for the discrete random variable. That's the case. Is that okay? And we try to check the probability, then you can see, oh, that's the way how we try to do that. Any questions for this one? Do I need to show another discrete random variable? Oh, why? Oh, so because we try to generate, like you can consider we input this is a function. So we try to input the random number with the uniform 10 to the 4. And then I try to generate that, and to get this y, this is the quantile. So y will be either 0, 1, 2, 3. And we want to check for each of them, does each of them have the same probability as them be assigned? So 0 should close to 0.2, and 2 should close to 0.4, and 2 should close to 0.3, and the last one should close to 0.1. Of course, it will have some difference, but it will follows like the general pattern there. So this is to verify. So you can do the same thing, like, okay, you know how to generate this random variable based on this inverse distribution method. Okay, you have some x and you have the new y, and then you try to, based on the standard uniform, to generate your y. But how can you verify it? You will check, like, for example, choose a little bit large sample size, 10 to the 5, 10 to the 4, and then you check the probability, because this is the massive function you get, and probability mass function you get, and then you try to check if that's like satisfy the condition you'll be given there. Okay, so discrete is not so complicated, especially when you try to map it back. Okay, then I want to show you something a little bit different, but it's like for the continuous, it's a very simple case. And this will also help us to understand how can we map the uniform. I will choose a very simple case to show you how we can do that for the continuous case. Okay. I think it will be interesting, even though I think it will be okay for 10 minutes. So let's just consider a uniform distribution, okay? Like, I just want to use that as an example, so it will be easy to get it. So just like do it, the uniform distribution are on the interval -1 to 1. So for this case, we don't try to do the uniform mapping directly. We try to consider use this inverse transformation, inverse distribution transformation to do that. Then how should we do it? Okay, so here, there is a simple case. Suppose this x -1 to 1. Okay, I just want to illustrate the idea. Even though you can argue, oh, we can easily do it. Of course, let's just consider how we can use the inverse distribution function, like this method, to do this. So what is the density of this x? 1/2, right? Okay. Okay, then let's try to find the CDF, so which means f. Okay, I cannot use our t. I can not use x because this is CDF, so f of x should equal to something like this. Okay, and then this will be plug this inside, right? So we get this is x plus 1 over 2. Is that okay? So this is our cumulative distribution function. And of course, here we need to have something is this is from -1 to 1. If x is less than -1, 0, x is greater than 1, that's 1. This is a cumulative distribution function, right? Okay, then we actually try to play with that part is here. So suppose we have some z. Satisfy the uniform, a standard uniform, and then I try to get some little z. Okay, because it's continuous, so z is f of x. Okay, and then we try to figure out x is equal to f inverse of z. Right? This is the inverse distribution function we try to do. So here, let's plug it inside. This tells us x is 2z minus 1. Very simple derivation, right? Nothing fancy here. So this tells us it will be 2z minus 1. So we get this is the inverse function. So how can we try to get this x based on this uniform? We just need to double it and -1. And actually, that's exactly the shifting we can do, right? So 0, 1. So if we have some points here, because right now this is from -1 to 1. So we're just stretching it. So times 2, then we will get, if we times 2, then we should get some points to here, but then it will be 0 to 2, and then do -1. So we shift it to here. Okay. Why we shift? Because -1, so shift it to the left. That's the case. Because we from 0 to 2, so you can consider you shift this -1, so 0 will be -1, 2 will be 1. So the whole interval goes to that way. Is that okay? So here actually give us the idea how we can try to do, like use the inverse distribution function. We actually get the same idea as we do for the uniform. I show this example because this one is a simple one and can illustrate how we try to find an inverse function, like here. And of course, this one is easy to do. Or like I can make it a little bit more complicated, but not every time like you can. I can also try to create something other than that, do some like density function. We can see it. But this one is the simpler case. So you can try to do, and when you get the cumulative distribution function, you just need to do the inverse and figure out this inverse. And of course, we know this is the cumulative, or maybe let's see the graph. It will be a little bit clear instead of do the shifting. So let's see. So this is -1, this is 1. So of course, the cumulative distribution function is somewhere here and 1 here. And then it's 1/2, so that's the slope. So you're trying to, it's kind of x over 2 plus 1/2. So you start from here. I just connect this. So when it's 0, so this will be 1/2. So no, this is the cumulative distribution function. And for this case, how can we try to get its inverse? So 2z minus 1. So here, be careful. Z should from 0 to 1, okay? So 2z minus 1. Okay, so z is 0. It's -1 here. And then this is 1. So 2z minus 1 and 12 looks like this. This should be 1/2. Okay, but here when I try to do that, this F inverse or this is F, I try to consider always this is X, this is Y. That's the input. So that's why I do that. Otherwise, it will just consider this case is just the directly one, because you can see the value it will cross is just from 0 to 1. That's it. You just map it back. So you will get the answer. Okay, so this is the continuous. If it's continuous, you just try to find the inverse. It will be easily to get that. If it's discrete, then you need to figure out a way to map it back, even though it's still not so complicated. Okay, so we can still try to do something like this. I want to leave you one question to think about how to do that. So for example, I still want to generate some random variable. Okay. So this random variable x, and I know this x actually is on the interval 0, 1. So we know its density is x squared, and it will have x's from 0 to, oh, sorry. The density is c times x squared, and then our x is from 0 to 1. Can you find the c? Okay, first find the c. Second, figure out a way to generate x based on this inverse or distribution transformation here. Figure out to generate. Okay, so 2 questions you can think about. This is a very simple one. You first need to show this is a density function, which means you need to integrate that on the interval 0, 1, that should be 1. Okay, and then you can find the constant c. And then based on that, find a cumulative distribution function, and then do the inverse. And then you use use the uniform, standard uniform, then you can generate this x. That's idea. Try to think about that. Of course, you don't need to or do it, but that's something very simple. You can try to practice if you really understand this like inverse distribution method. Okay. Or the density, no, the density is c times x squared. But c is a constant. Find this constant c. Because right now I don't have, I know it should not be 1 if it's on 0, 1. Otherwise, otherwise the probability is not 1 if you integrate that from 0, 1. But I didn't remember the exact value, so I put the c here. You will see similar question. Like I can always do that. Say I don't know the exact constant, but put a constant there to verify this is a density function. So density function will integrate on the domain, so it will equal to 1. That's the continuous random variable case. Okay. All right. Yeah. Or you can always find a Jamboard here, so you can try to do this one. Then next week, then we will go back to this, and I'll try to design some other questions. You will see the second homework. Okay. All right. Any questions? Okay. Thank you. Have a nice weekend. See you next week. Yeah.